Alright, let's put our flashlight where our mouth is. We've traded in the cardboard wall of childhood imagination for a subtler concept, the observable universe. It's the part of the cosmos that we can see because light, or, if you're generous, other messengers like neutrinos and gravitational waves, has had enough time to make the trip to us. Think of it like this. You're at a concert, standing somewhere in the crowd, and the band launches fireworks. If you're close, you hear the crack instantly. If you're in the back, there's a delay. The sound takes time to reach you. Now imagine the band started playing not at 8 p.m, but at the dawn of time itself. That's the situation we're in with light. The band is the universe, the stage lights are galaxies, and we're stuck somewhere in row 13.8 billion, waiting for the photons to catch up. But here's the thing. The math doesn't stop at 13.8 billion light years. That's the rookie mistake. Because while those photons have been on their way, space itself has been stretching like taffy. So the stuff that emitted the light back then is now way farther away than just 13.8 billion light years. By the time we receive it, the expansion has carried those galaxies outward. What we end up with is a visible bubble much larger than you'd think. How large? Hold your breath. About 93 billion light years across. Let me repeat that, because it's the kind of number that should cause minor heart palpitations. 93 billion light years across. That's the diameter of the observable universe. From where you sit or stand or lie awake with your phone in your hand, the farthest light we can detect comes from a sphere stretching 46 billion light years in every direction. Now pause. Let your brain misfire for a moment. The universe is 13.8 billion years old, but we can see 46 billion light years away. What sorcery is this? The culprit is the expansion of the universe. Space has been growing under the feet of those photons as they travelled, so the source of the light we catch today is much farther than a simple time x speed of light calculation would suggest. It's like trying to walk across a treadmill while someone keeps increasing the speed beneath you. The ground itself is conspiring against your progress. And yes, you sit at the centre of this bubble. Don't let it go to your head. Everyone else does too. If you hop over to Andromeda and ask the same question, you'd get a different bubble with Andromeda at the centre. Still about 93 billion light years wide. Every galaxy carries its own observable bubble like a lantern in fog. From the inside it looks like the whole world. But from outside, well, there is no outside. That's the whole trick. The idea that you're at the centre of the universe has historically been a bit embarrassing. Humans have fallen for that one before. Ask Copernicus. But this isn't geocentrism sneaking back in through the back door. It's geometry. Wherever you stand, the observable universe radiates outward around you, because what you're measuring is distance light could have travelled since the beginning. You're not special. You're just equally trapped by the rules of physics as everyone else. And maybe there's some comfort in that. When you look at the cosmic microwave background, the afterglow of the Big Bang, you're staring at a wall of light 46 billion light years away. That's as far as photons have gotten since things kicked off. Beyond that, we can infer, we can hypothesize, we can even model, but we cannot see. It's not a limitation of telescopes or budgets. It's a limitation of causality itself. This is what cosmologists mean by the edge of the observable universe. It's not a brick wall, not a line of no entry tape. It's the horizon of the knowable. Beyond it, reality may continue forever or loop back on itself or do something so strange we haven't even invented the math yet. But here's the kicker. That boundary moves. As time passes, light from farther regions has time to arrive. Our observable bubble grows, slowly, inexorably, like a drip filling a bowl. Of course, there's a cosmic catch. While we wait for new light to come in, space expansion keeps hustling galaxies away. Some of them are already lost causes, racing away faster than light can keep up thanks to the stretching of space. We'll never see them, no matter how patient we are. It's like waiting for a train that has already left the track you're standing on. The station is gone, and you didn't even hear the whistle. So here we are, lodged inside our own bubble of visibility, 93 billion light-years wide. And yet, that's not the whole story. Not even close. Because what we're seeing isn't the real present-day state of the universe, it's the universe as it was. Old news, fossils in light, which raises a stranger, more mischievous question. If this is just the observable patch, what's hiding beyond it? That's where the conversation gets slippery, because beyond the horizon isn't just unseen, it's unseeable. And that's where imagination either collapses in frustration or thrives in wonder. Next, let's tilt our heads toward the very limit of our sight, the cosmic horizon itself, the ultimate you can't go past this level screen in the arcade game of reality. So let's walk right up to the edge of our cosmic eyesight, the horizon of vision, the farthest distance from which light has managed to sneak into our telescope since the beginning. This isn't a poetic horizon like the sea at sunset. It's a hard law of physics horizon, written in the ink of time and speed. Here's the deal, the universe is about 13.8 billion years old. That means the farthest light we should be able to see is 13.8 billion light years away, because nothing can outrun light, right? Wrong. The fine print always ruins the headline. The universe is expanding while that light is in transit. So what started as a short commute for those photons turned into a marathon on an ever-stretching track. By the time their little marathon ends at your eyeball, the galaxies that release them have been carried far, far away. That's why the true radius of our observable universe isn't 13.8 billion light years, it's about 46 billion. Let me throw you an image. Imagine you're in a boat, tossing a message in a bottle to a friend on the shore. While the bottle floats, the tide sweeps the shore farther and farther back. By the time your friend finally picks it up, they're standing way farther from you than the distance you initially threw it. That's what's happening with the cosmic horizon. And here's the mischievous twist. That horizon is not a fixed border. It's more like the bubble in a lava lamp. It moves. Every second, new light is arriving at Earth from deeper and deeper into the past. That means your personal observable universe is expanding very slowly every day you're alive. Right now, as you're listening, photons that left their galaxies 13.8 billion years ago are finally hitting us. Tomorrow a few more will trickle in. You're constantly receiving very old mail. But don't get too excited. This isn't a subscription box that never ends. Some galaxies are moving away from us so quickly, thanks to the accelerated expansion driven by dark energy, that their light will never reach us. They're retreating faster than the universe allows light to chase them. It's not that light slows down, it's that space itself is sprinting away under its feet. These galaxies are like party guests who slipped out before you even knew they arrived. No matter how powerful your telescope, no invitation will bring them back. Now, here's where philosophy sneaks in wearing a lab coat. Beyond this horizon, beyond the place light hasn't had time to reach us yet, what happens? Does space stop? Does reality end like a badly drawn map with "Here be dragons" scrawled across the blank? Or does it go on forever, unbothered by our inability to see it? Every sign we have points to the second option. The universe doesn't politely end where our eyesight does. Our horizon is not its horizon. It's just the limit of our conversation with it. Think of it like sitting in a dark field at night with a lantern. The glow of your lantern defines a circle of grass and trees around you. Beyond that circle, more forest, more night, maybe more wolves. The forest doesn't stop at the boundary of the light. It just stops being your forest. That's the observable universe. The lantern is the speed of light. The forest is everything else. And this little truth should rewire how we ask questions. When people talk about the end of the universe, what they're really brushing up against is the end of their personal bubble of light. It's not a place you can travel to. You can't hit the wall like Truman in The Truman Show and push your way into a backstage set. It's not a structure waiting to be discovered. It's a limit waiting to be respected. But of course, humans being humans, we still itch for the word edge. We want to know, if there's a horizon, can we cross it? Can we cheat? Can we build a telescope so absurdly big, or wait so absurdly long, that we finally see the real end? The sobering answer is no. Light has a union contract. It works only as fast as it can. And even though time will keep adding new slices of sky to our field of view, the expansion of space means we're also losing ground. Some galaxies are already disappearing forever from our sight, like ships dipping below an ocean horizon, except in this ocean, the water is swelling in every direction. So this is the bargain. The horizon of vision is not a wall, not a fence, but a moving line drawn by the universe's age and light's stubborn speed. It grows as we grow, yet never enough to reveal the whole. It hides more than it shows. It teases with the suggestion that out there may stretch without limit, and that we, tiny primates with telescopes, will never catch all of it. And just when you've wrapped your head around this bubble, the universe plays its favourite trick. It says, "Oh, you think you understand me now? Wait until you hear how big the bubble actually is." 93 billion light-years across. A sphere so vast it makes galactic feel like a neighbourhood watch group. That's where we're heading next. The part where we stop whispering about horizons and start yelling about scales too rude for human intuition. Take a deep breath. Ready? Because now we need to do violence to your sense of scale. The observable universe, that little lantern glow we just described, isn't a cosy 13.8 billion light-years across, like your intuition might suggest. No, it's roughly 93 billion light-years wide. That's not a typo. That's the diameter of the cosmic bubble we live in. Imagine a sphere so large that if you tried to cross it at the speed of light, which is already the absolute maximum speed allowed by the laws of physics, it would still take you 93 billion years to get from one side to the other. And remember, the universe itself is only 13.8 billion years old. The math feels insulting, doesn't it? Here's the cosmic joke. The expansion of space. Light left distant galaxies billions of years ago, but while it was en route, the fabric of the universe stretched beneath it. By the time that light arrived at our telescopes, the galaxies that sent it had been carried far away on a conveyor belt of expanding space. So when we talk about how far they are now, it's not 13.8 billion light-years, it's 3 times that. Picture this. You're standing on a moving walkway at an airport trying to toss a paper airplane to your friend at the other end. The plane glides smoothly, but while it flies, the walkway itself is rolling backward. By the time your airplane finally lands in their hand, the friend has been carried way farther away than when you first threw it. That's what's happening on a universal scale, except instead of a paper airplane, it's photons. And instead of an airport, it's all of space-time. Now, here's where the human ego gets gently dismantled. From our perspective on Earth, we seem to sit smack dab in the middle of this 93 billion light-year sphere. But that's not because we're special. That's because everyone is in the middle of their own sphere. If you're on a planet orbiting a star in a galaxy 10 billion light-years from here, you'd measure the same thing. A bubble of 93 billion light-years in diameter centered on you. Every observer carries the illusion of centrality, like an optical trick the universe plays to keep us humble, or maybe entertained. This raises an unsettling but freeing truth. There is no universal center, no cosmic capital city, no downtown hub of the cosmos with smaller suburbs spiraling out. Every point is as central as every other. The observable universe is just a patch of the whole thing, a patch shaped by your location and by time itself. It's tempting to ask, if we're in a 93 billion light-year bubble, what's outside the bubble? But the question is a trap. The bubble isn't the universe, it's just the part visible to us. Beyond it may lie more galaxies, more clusters, maybe infinite repetitions of everything. The bubble doesn't contain reality. It contains our view of reality. Think of standing in a fog. The circle of visibility is not the forest itself. It's just the limit of what your eyes can pierce. Beyond it, the trees go on. And here's a thought experiment to really make your head tilt. What if there are civilizations on galaxies at the rim of our observable universe? Their bubble of sight would overlap with ours a little, but extend in directions we can't see. They'd look up at their night sky and argue in their philosophy classes about whether the universe has an edge, just as we do. To them, we are part of the invisible beyond, galaxies forever hidden behind their horizon. So the edge of the universe is plural, it's personal. Everyone gets one, but no one gets the edge. It's like an infinite multiplayer game where each player is locked inside their own glowing orb of visibility. No orb is more privileged than another. The cosmos doesn't play favourites. At this point, it should feel obvious that words like end and boundary don't map well onto the universe. Our language evolved to talk about kitchen tables and city walls, not expanding space-time. Yet there's a thrill in this mismatch. The moment your intuition collapses is the moment you're forced to let science redraw it. That's why cosmology feels less like memorizing facts and more like therapy. It teaches you to stop clinging to edges. But don't get too comfortable. If there's no center and no boundary in this 93 billion light-year balloon, what does it mean to say the universe is expanding? What is it expanding into? Is there an outside, a background canvas, or is the whole idea of outside nonsense when applied to everything? These are the kinds of questions that keep even professional cosmologists awake at night. And that's where we're going next, into the paradox of an expanding universe without a center, without an edge, and without an outside. Get ready to meet the balloon and the raisin bread. Two analogies that will either enlighten you or ruin baked goods forever. Here's where things start to sting. We've built our little 93 billion light-year bubble, admired it from the inside, and maybe even bragged a little about how big our universe looks. But now comes the painful correction. We're not in the center. Not really. Nobody is. Let me explain. Imagine standing in the middle of a vast field, and fog stretches out in all directions. From where you stand, the fog wraps you in a perfect circle. You can't see past a certain point, and it feels like you're in the middle of everything. But walk 100 meters in any direction and surprise, the horizon of visibility moves with you. Every new spot looks like the center of the fog. That's the observable universe in a nutshell. It's tempting to believe there's some absolute downtown of the cosmos, the cosmic Times Square, bustling with galaxies while everything else sprawls out from there. But no such place exists. Expansion isn't like an explosion where debris scatters from a single origin point. It's more like dough rising in the oven, with raisins, galaxies, embedded inside. As the dough expands, the raisins all move away from one another, and each raisin could claim to be the center of the action. This is why our own Milky Way isn't particularly special in a geometric sense. Sure, it's home, and yes, we're attached to it sentimentally. But cosmologically speaking, it's just one raisin among hundreds of billions, and every raisin, from the most elegant spiral galaxy to the scrappiest dwarf galaxy, can look around and claim, I'm in the middle of the universe, and they'd all be right. So the phrase, the edge of the universe, becomes slippery. It's not a place you can travel to. It's not a finish line with a checkered flag and cheering crowds. It's just the current limit of your own vision. Move somewhere else, and your personal edge moves too. The universe doesn't have a single universal border. It has as many edges as there are observers. Here's the delightful paradox. Our smallness and our ordinariness are universal. Nobody gets to be the cosmic favourite. And in a strange way, that makes us kin with every alien astronomer who has ever squinted at their own night sky and wondered the same thing. From their perspective, we are beyond their horizon, just as they are beyond ours. Every species is trapped inside its private bubble of light, waving at shadows of the past. This idea unsettled astronomers for centuries. Ancient cosmologies loved to put Earth at the centre. Even when Copernicus, Galileo, and Kepler pushed us out of that central throne, we still wanted something to play the role of cosmic anchor. But the universe is less sentimental. It says, there is no anchor, no throne, no central spotlight. There is only expansion everywhere, and horizons for everyone. And here's where it gets weirder. If the universe doesn't have a privileged center or a privileged edge, then asking where does it expand to becomes a nonsense question. Expansion isn't like air rushing into an empty room. It's not growth into something else. It's the stretching of space itself. No outside, no container. Just the fabric of reality becoming more fabric. It's a truth that tastes bitter at first sip. We crave edges and centers because they give us narrative closure. They let us say, that's where it begins, that's where it ends, and this is the middle. Without them, we're left adrift, but keep sipping and the bitterness turns sweet. Because a universe with no privileged place is also a universe where our little corner, however ordinary, is just as valid a vantage point as any other. We're not at the edge of the stage watching the show. We're woven into the stage itself. And if you're still itching for metaphors, don't worry. The universe has some favourites prepared. Next, we'll call in the balloon and the bread loaf. 2 culinary thought experiments that will ruin your next snack, but save your intuition about cosmic expansion. Okay, time to ruin the night sky for you in the best way possible. For most of human history, people thought the stars were fixed. Tiny lamps hanging from some great dome, maybe twinkling because angels got bored and wiggled them around. Then along comes Edwin Hubble in the 1920s, peering through a telescope big enough to scandalise the neighbours. What he saw changed everything. The galaxies weren't just sitting there, they were moving, and worse, they were moving away from us. At first glance, this feels like cosmic arrogance. Oh, so everyone's running away from Earth specifically? But no, Hubble discovered something subtler. The farther away a galaxy was, the faster it seemed to be retreating. The redshift in their light betrayed it, like a siren's wail dropping in pitch as the ambulance speeds past. This wasn't about galaxies hating us. It was about space itself stretching, pulling them apart like dots on a rubber band being tugged at both ends. This is where analogies earn their keep. Picture a balloon. Now draw a bunch of dots on its surface. Those are galaxies. Start inflating the balloon. Every dot sees every other dot moving away, and the farther the dot, the faster it recedes. There's no central dot, no cosmic kingpin. The expansion is everywhere equally. That was Hubble's gift to us. The realization that the universe itself is a kind of restless fabric, unwilling to sit still. And this isn't just a trivial factoid, it's the foundation of modern cosmology. The expansion tells us the universe once was smaller, denser, hotter. It's the smoking gun of the Big Bang, the reason we can speak with some confidence about a beginning at all. Without expansion, the night sky would just be a static wallpaper. With it, we get history, drama, and yes, an expiration date. But here's the real headache. What is the universe expanding into? If the balloon grows, doesn't it expand into the room around it? That's what your intuition screams. Yet physics gives you a cold no. The balloon surface isn't expanding into anything, it's just stretching. The 2-dimensional ants living on that balloon don't need to imagine a third dimension. For them, space simply grows beneath their feet. Likewise, our 3-dimensional universe doesn't need an outside to expand into. It just does. Expansion is not motion through space. It is the growth of space itself. And that's why Hubble's discovery was such a gut punch. It wasn't just that galaxies were far away. It was that the very ruler we use to measure distance is unreliable. Imagine if every time you tried to measure your living room, your tape measure quietly grew longer while you weren't looking. That's what space is doing to us. Expansion means distance is a moving target. The kicker? This expansion isn't slowing down. Thanks to the mysterious nudge we call dark energy, it's actually accelerating. That means distant galaxies aren't just drifting away politely. They're sprinting out of our cosmic neighbourhood, eventually crossing the horizon of visibility, never to be seen again. The sky of the far future will be emptier, lonelier, stripped of the galaxies we now take for granted. But let's not rush there yet. For now, sit with Hubble's revelation. The universe is dynamic. It grows. It evolves. It refuses to be static. And once you accept that, a new question creeps in through the back door. If it's expanding, does it have a shape, a curvature, a destiny written in geometry? That's where the balloon meets its cousin, the loaf of bread, and trust me, you'll never look at breakfast the same way again. All right, time to mess with your pantry. If the balloon analogy hasn't already bent your brain, let's inflate it a little more. Picture yourself as a tiny ant crawling on the surface of that balloon. You don't know about the rubber or the air inside. To you, the balloon's surface is the entire universe. You walk forward and you never find an edge. You walk sideways, still no edge. And when the balloon inflates, every spot on that rubber skin moves farther from every other spot. From your ant's eye view, the universe is expanding, without a centre, without an outside. Now here's the key. That surface has no privileged point. No ant can say, aha, this is the middle of the balloon. Because the middle doesn't exist on the surface. The balloon's centre is in a dimension the ants can't even imagine. That's us. We're the ants. The balloon is space-time. The outside is something we're not equipped to define. But balloons have one flaw as analogies. They suggest a hollow outside, and our brains immediately start to picture the universe swelling into some cosmic living room. Physics tells us to resist that urge. The expansion of the universe doesn't need a container. It doesn't push into anything. Space itself is the fabric being stretched. There's no room beyond the room. The room is all there is. If balloons aren't your thing, let's switch to breakfast. Imagine a loaf of raisin bread dough rising in the oven. The raisins are galaxies. As the dough swells, the raisins all move apart. None of them is the centre. Each raisin looks around and sees its neighbours receding, and the farther away the raisin, the faster it recedes. That's the Hubble law baked fresh, ready for butter. The bread analogy also makes a darker point. The raisins aren't moving through the dough. They're being carried apart because the dough itself expands. If you were a raisin complaining about your neighbour drifting off, you'd have to blame the bread, not the neighbour. Both metaphors, balloon and bread, teach us the same uncomfortable lesson. Expansion isn't about galaxies travelling across a static void. It's about the void itself growing, dragging everything along with it. It's as if the universe has an elastic waistband and it keeps ordering dessert. And here's where the unease sets in. If the universe is expanding everywhere at once, then the question, what is it expanding into, doesn't just lack an answer, it lacks meaning. It's like asking, what's north of the North Pole? The words make sense separately, but put together they become nonsense. Expansion isn't relative to an outside, it's relative to itself. Now this doesn't stop us from trying to imagine it. Our brains are stubborn little storytellers. We picture the balloon floating in a room, or the bread swelling in an oven, but those extras, the room, the oven, are just scaffolding for our limited intuition. The universe doesn't need them. Space stretches because that's what space does. No outside required. And if you're starting to feel a little betrayed, you're not alone. Humans are wired to expect walls, edges, containers. We like our fish tanks. Cosmology tells us we're not in a tank at all. We're in the water itself, and the water has no shore. So where does that leave us? We know the universe expands. We know it has no edge in the way furniture does. But what about its ultimate shape? Is it curved? Flat? Closed like the balloon? Open like a saddle? Or something so strange our metaphors won't survive? That's the next step in this late-night walk, peeking into the geometry of everything. All right, let's slow down and poke this beast with a stick. What do we actually mean when we say the universe is expanding? Because if you're anything like me, the word expanding instantly paints a picture of galaxies zooming through a black void, like cars speeding down a cosmic freeway. That picture is wrong. Beautifully wrong, but wrong nonetheless. Expansion doesn't mean the galaxies are racing through space. It means the space itself is stretching. The galaxies are like dots painted on a rubber sheet. The sheet expands and the dots drift apart without ever moving across the sheet. From their point of view, they're just chilling where they've always been. It's the universe underneath them that won't sit still. Here's an analogy with a twist. Imagine you own a tape measure. One day you measure your desk and it's a solid 1 meter. You walk away, come back an hour later, measure again, now the desk reads 2 meters. Did the desk grow? Not exactly. Your tape measure stretched. That's cosmic expansion in a nutshell. The very ruler we use to measure distance is itself changing. And it's not polite about it either. Space stretches everywhere all at once, indifferent to your desire for stable ground. If you point a telescope at a galaxy, you're not just looking into distance, you're looking into time. The light left that galaxy billions of years ago, and while it made the journey, the road itself lengthened under it. That's why the galaxy is now much farther away than the age of the light implies. This also explains one of the strangest predictions of cosmology. Some galaxies we see today are already beyond our reach. Their light managed to leave before space accelerated too much. But the galaxies themselves are now racing away faster than light can keep up. That's not because they're breaking the cosmic speed limit. No one's slapping galaxies with speeding tickets. It's because the limit applies to motion through space, not to space itself stretching. Space cheats. And here's the part that makes astronomers both excited and a little sad. The expansion isn't slowing down. It's accelerating, thanks to something we call dark energy. A placeholder term for, we don't know what the heck this is, but it's bossing the universe around. Because of dark energy, the galaxies we see today will, over billions of years, slip out of our observable bubble. Their light won't be able to keep up, and the night sky of the far future will look emptier, lonelier. Future astronomers, if any exist, will inherit a cosmic desert, stripped of evidence that we live in a vast dynamic universe. They'll look up and see only a handful of local stars and wonder if all those old legends about galaxies were just myths. This is why the present moment in cosmic history is weirdly privileged. We live in the brief window when the universe is old enough to be filled with galaxies, but not yet so old that most of them have vanished beyond the horizon. We can measure, compare, and understand because the evidence is still here. It's like showing up to a party at the one magical moment when everyone is dancing, the snacks aren't gone, and the music hasn't been shut down by the neighbours. A few billion years earlier the room was too small and chaotic. A few billion years later the room will be half empty. We've arrived at the sweet spot. So, expansion isn't just trivia. It's fate. It shapes what we can know, what we can see, and what will one day be erased from memory. And it sets up an even bigger, juicier question. If the universe is expanding, then what happens at the very beginning? How did the expansion kick off, and why did it unfold the way it did? That, my friend, leads us straight to one of the most dramatic events in all of science. Cosmic inflation, the universe's hyperactive growth spurt in its first fractions of a second. The story of inflation is equal parts detective work and fever dream, and it's the reason we can say the universe is as smooth, flat, and big as it is today. Here's the part where the universe starts playing the ultimate magic trick. It makes galaxies disappear, not with a puff of smoke or a magician's flourish, but with the slow, relentless creep of physics. Remember how we said the universe isn't just expanding, it's accelerating. That's thanks to dark energy, the mysterious force, or maybe property of space itself, that acts like cosmic caffeine, speeding everything up. Because of this acceleration, galaxies that are currently visible to us won't stay visible forever. One by one, they'll slip over the cosmic horizon and vanish from our sky. Imagine you're standing on a beach, watching ships sail away. At first, you can see them shrinking on the horizon, their masts still poking above the waterline, but then, inevitably, they dip below the curve of the Earth. Gone. You know they're still out there, but your eyes can't confirm it anymore. Now take that melancholy feeling and multiply it by billions. That's the fate of galaxies in an accelerating universe. Some of them are already beyond saving. Their light left ages ago, barely reaching us now, but the galaxies themselves have been carried so far away by expansion that no new light from them will ever make it here. It's like getting the last letter from a friend who has since moved into a neighbourhood you can't access, no matter how long you wait at the mailbox. Here's the part that really messes with your heart. The night sky is temporary. When we look up and marvel at the faint smudges of distant galaxies, Andromeda, the Whirlpool, the Sombrero, we're catching them in the small, privileged window of time when they're still within reach. Fast forward 100 billion years, and the sky will look shockingly barren. Future astronomers, if they exist, will see only the faint halo of our local group of galaxies. Everything else will be gone, erased from the observable record. That means we're living in a golden era of cosmology. We can still measure the redshift of galaxies, still detect the cosmic microwave background, still trace the fingerprints of the Big Bang. Our descendants, assuming any are still around, won't be so lucky. To them, the universe will look static, empty, eternal. They'll have no evidence of expansion, no proof of a fiery beginning. They might conclude the cosmos had always been that way. In other words, we might be the only generation in cosmic history that can truly know where we came from. It's almost cruel, isn't it? The universe hands us the clues, but only briefly. It's as though the cosmos itself is whispering, "Look now before I hide the evidence," and this realization forces a weird kind of humility. We always think of ourselves as latecomers, tiny specks who arrived billions of years after the action started. But in a cosmic sense, we're early birds. We showed up just in time to see the show before the curtain falls. So where does this leave us? With a bittersweet awareness. The galaxies we see aren't forever. They're postcards from the past, slipping out of our reach even as we admire them. And yet knowing this makes them feel more precious, doesn't it? Every dot of light in the night sky is a fleeting guest, a brief companion in our cosmic story. But if galaxies vanish over the horizon, what about the beginning itself? How did the universe get the jump start that set all of this in motion? That's where we stumble into the strangest chapter yet. Cosmic inflation, the universe's baby picture, taken in the first split second of time. All right, buckle up. Because if you thought galaxies slipping over the horizon was unsettling, wait until you hear how the whole thing began. Our universe, it turns out, wasn't content with a quiet start. It went through a phase so absurd, so violent, that every metaphor we try to use feels like bad poetry. This is the story of cosmic inflation. Here's the short version. In the first fraction of a second after the Big Bang, about 36 seconds, if you like your numbers small, the universe grew faster than your imagination can handle. Space itself ballooned, expanding not just at the speed of light, but exponentially faster, doubling in size again and again in a cosmic heartbeat. In that blink, the universe went from subatomic to something you could measure in meters, then kilometers, then light years, before you could even finish your first thought. Why invent such a wild story? Because without inflation, the universe doesn't make sense. Without it, the cosmos we see today, smooth, flat, uniform in every direction, should be a mess. Galaxies should be clumped, the cosmic microwave background should look chaotic, and the very geometry of space should curve like a funhouse mirror. Instead, it's astonishingly even, like someone ironed the wrinkles out of reality. Inflation is that iron. Here's one way to picture it. Imagine a balloon with permanent marker scribbles all over it. At first, the scribbles are sharp, chaotic, obvious, then blow the balloon up in an instant. Suddenly those wild lines stretch smooth, the wrinkles flatten. From far away, the balloon looks calm and uniform. Even though up close you know it started as chaos. That's what inflation did to our universe. It took a tiny, lumpy beginning and stretched it so brutally that it became smooth on the larger scales. And inflation didn't just smooth things out, it set the stage for everything we see. The tiny quantum jitters, microscopic fluctuations in energy, were blown up to cosmic size. Those ripples became the seeds of galaxies, clusters, and ultimately you and me. In other words, the universe's largest structures are built on the scaffolding of quantum uncertainty. We are quite literally children of fluctuations. Here's the kicker. Inflation also explains why the universe looks the same in every direction. Without it, distant regions of space would never have had time to talk to each other, to share temperature and density. They should look completely different. Yet the cosmic microwave background shows uniformity to a mind-boggling degree, like a cake baked to exactly the same temperature throughout, even though half the oven was never in contact with the other half. Inflation solves that by insisting, once everything was close together, then space stretched faster than light could travel, freezing that sameness across vast distances. Now, before you ask, no, this doesn't break Einstein's speed limit. Nothing moved through space faster than light. Instead, space itself expanded. Einstein's cosmic speed limit is safe. It's just that space found a loophole in the contract. Of course, with every answer inflation provides, it sneaks in bigger questions. Why did it start? Why did it stop? And what if, brace yourself, it didn't stop everywhere? Some versions of inflation theory suggest our universe might just be one bubble in a frothy multiverse, with new universes inflating endlessly like cosmic champagne. If that's true, our entire observable universe, 93 billion light-years across, is just one bubble in an infinite sea. That's a thought heavy enough to keep you awake long past midnight. But whether or not the multiverse exists, inflation remains our best explanation for why the universe looks the way it does. Smooth, flat, vast, and full of galaxies instead of chaos. So, inflation gave us the stage, but we still haven't answered the most tempting question. If the universe is expanding, does it ever end? Does the balloon eventually run out of rubber? Or is it infinite, unbounded, a story without a last page? That's where we're headed next, into the geometry of everything, and whether space itself is finite, infinite, or just mocking us with illusions. All right, let's circle back to the itch that never goes away, the one that's kept philosophers, poets, and physicists up at night. If the universe is expanding, surely it must be expanding into something. Surely there must be a rim, a final stop, a border you could in principle crash into if you travelled far enough, right? Here's the cold answer from modern cosmology. No edge, no wall, no finish line. It's a hard pill to swallow because our instincts scream the opposite. Every human experience is boxed in. Rooms have walls, maps have borders, even oceans, vast as they feel, still wrap around continents. But when we try to extend that logic to the universe itself, the logic breaks. Space doesn't end, it bends. Think of Earth. Our planet is finite, yes, but if you start walking in any direction, you'll never find the edge of Earth. You'll just loop around, eventually ending up where you started. The surface is closed and finite, but unbounded. No cliff, no edge, no here it ends. Now take that concept, crank it up into 3 dimensions, and you get one possibility for the universe. It might be finite in volume, but still have no edge, no border to bang your head on. On the other hand, maybe the universe is infinite. That possibility is even harder to chew on. Infinite means you can pick a direction, walk forever, and never come back around. It means endless galaxies, endless stars, endless repetitions of cosmic scenery. In that case, the very word edge loses meaning, because infinity doesn't allow for endpoints. Here's the trouble. Both scenarios, finite but unbounded or infinite and edgeless, look the same from our tiny bubble. The observable universe doesn't reveal whether the cosmic stage eventually loops like a globe or stretches out endlessly like a desert. For now, we're stuck peering at patterns in the cosmic microwave background and hoping the data will whisper a clue. But there's one thing we can say confidently. The universe doesn't end where our observations end. Our 93 billion light-year bubble is not the wall of the cosmos. It's just the wall of our sight. Beyond it, space keeps going, whether that going is finite or infinite. And if you're tempted to imagine the edge as a physical wall with a giant "the end" sign, remember this. Even if the universe were finite, there wouldn't be a brick border. It would simply curve back in on itself. The edge would be an illusion, just as Earth's flat horizon turned out to be an illusion. So, is there an edge after all? No, at least not in the way your kitchen table has one. There's no cosmic cliff waiting to drop you into nothingness. Instead, the universe might be a kind of closed loop, or it might be an endless expanse. Either way, the edge we crave doesn't exist, and that leaves us with another question. An even stranger one. If there's no edge, and maybe no boundary, then what possibilities come with an infinite universe? What if infinity means not just more galaxies, but every possible galaxy, every possible version of history, every possible you? That's where we head next, into the unnerving, exhilarating territory of infinite possibility. So here we are, staring down the most vertigo-inducing idea of all, infinity. Not the poetic infinity scribbled in a love letter, not the lazy infinity of forever yours. I mean the hard, mathematical, merciless kind, the kind that doesn't end, doesn't loop, doesn't soften, an infinite universe. If space really does go on without end, then every patch of the cosmos is mirrored by another, and another, and another, stretched out endlessly in every direction. It's not just more galaxies than you can count. It's galaxies without limit, clusters without limit, stars without limit. You could spend eternity counting and still not reach the bottom of the list. But infinity has a nasty habit of smuggling in consequences. If the universe is infinite, then probability gets drunk. Because in an infinite canvas, anything that can happen not only will happen, it will happen endlessly. Think about that for a second. If there are infinite stars, infinite planets, then somewhere, on some world, there's another version of Earth. Not just a copy with similar trees and oceans, but an Earth where the entire history unfolded the same way, down to your parents' meeting, your childhood crush, the embarrassing thing you said in high school. Somewhere out there, an infinite number of yous are living the same life, while an infinite number of other yous are making slightly different choices. Sounds like science fiction, right? But mathematically, it's not crazy. If the universe is infinite, then the arrangements of particles eventually repeat, just like rolling dice long enough ensures every combination shows up. Infinity guarantees duplicates, not once, but endlessly. And if that hasn't fried your circuits, here's the kicker. It also means versions of you exist who made every possible different choice. A you who never left your hometown, a you who became a professional ice sculptor, a you who's currently watching this video but paused it halfway to make a sandwich. All of them, scattered across infinity. This idea unsettles people, and understandably so. It robs us of uniqueness. If there are infinite copies, then what makes this you special? But let me whisper the counterpoint. Specialness doesn't come from rarity. It comes from being. The fact that you exist right here, right now, in this particular version of events is already extraordinary. Infinity doesn't cheapen it. It multiplies the wonder. And infinite space has other tricks. It means the universe is inexhaustible. Every galaxy you lose to the accelerating expansion, there are infinitely more beyond. Every night sky, no matter how stripped it becomes in the far future, is still embedded in a cosmos without end. The horizon might shrink, but the reality beyond it doesn't. Of course, science isn't done arguing. Some physicists hate the idea of infinite duplicates. Others embrace it, weaving it into theories of the multiverse. For now, we don't know if infinity is real, or if the universe is merely vast but finite. But the possibility alone forces us to grapple with the biggest question of all. What does it mean to live in a reality without limits? And to even approach an answer, we need a better handle on shape. Because infinity or finiteness isn't just a philosophical musing. It's written into the geometry of the cosmos. Curvature, density, topology. These are the clues that tell us whether the universe is a looping globe, a sprawling saddle, or a perfectly flat, endless plane. That's our next stop, the 3 possible cosmic shapes, and how we measure them using the oldest light in the universe. If infinity gave you a headache, geometry is about to add some aspirin and then snatch it away again. Because to answer whether the universe is finite, infinite, curved, or flat, we need to look at its shape. Not shape like a toy block you can hold in your hand, shape as in the curvature of the entire cosmos. In theory, there are 3 possible cosmic geometries. 1. Positive curvature, the spherical universe. Imagine Earth's surface, but in 3 dimensions. If you travel in a straight line long enough, You eventually loop back to where you started. That's a universe with positive curvature, finite in volume, but without edges. Like ants on a balloon, you never find a cliff. You just keep circling. In such a universe, parallel lines eventually meet, just as lines of longitude meet at the poles. 2. Negative curvature, the saddle-shaped universe. Now imagine a saddle, bending down one way and up the other. That's negative curvature. Space curves outward like a sprawling hyperbolic plane. Here, parallel lines never meet. They actually drift farther apart. This kind of universe is infinite, open, and forever expanding. In 2 dimensions, it looks like those Escher drawings where geometry defies your common sense, and every straight line seems to run away from you. 3. Zero curvature, the flat universe. Finally, the boring-sounding but most mind-bending option, flat space. A universe with no overall curvature, infinite in extent, where Euclidean geometry, the stuff you learned in school, still applies. Parallel lines stay parallel. Triangles add up neatly to 180 degrees. This one feels intuitive because it matches our daily lives, but don't let that fool you. Flat doesn't mean simple. It could still be infinite, or it could be finite with a funky topology. Like a video game map where walking off one side of the screen plops you back on the other. So how do we figure out which one is ours? Enter the idea of critical density. Think of the universe as a tug-of-war between gravity pulling everything inward and expansion pushing everything outward. If the actual density of matter and energy in the universe equals this critical density, space ends up flat. If density is higher, gravity wins, and space curves positively like a sphere. If density is lower, expansion dominates, and space curves negatively like a saddle. It's a delicate balance. In fact, so delicate that even a tiny deviation would, over billions of years, dramatically alter the universe's shape. Which raises an eyebrow. How is it that our universe hasn't spiraled into chaos, bent out of recognition by the smallest imbalance? This puzzle is known as the flatness problem, and spoiler, it's another reason why cosmic inflation is such a big deal. But for now, sit with the 3 possibilities. A universe shaped like a globe, a universe shaped like a saddle, or a universe that is flat as far as the eye can see. Each comes with its own destiny. A closed universe might eventually collapse back in on itself. An open one expands forever. A flat one toes the line in between. Its future dictated by forces we're still trying to name. So, which one is ours? To find out, scientists turn to the oldest light in the cosmos, the faint microwave glow left behind by the Big Bang. Hidden in that glow are patterns that act like fingerprints, revealing the curvature of the universe. And that detective work? That's our next chapter. All right, let's dig into the tug-of-war that decides the shape of the universe. At the centre of this cosmic game is something called critical density, the Goldilocks number that separates one geometry from another. Too much mass energy, and gravity curves space inward like a sphere. Too little, and expansion curves it outward like a saddle. Just right, and you get a flat cosmos balanced on the razor's edge. So what exactly is this density? Think of it as the average mass energy spread across the entire universe. Not just stars and planets. Those are barely crumbs. You have to count the invisible stuff too. The dark matter that clumps galaxies together, and the dark energy that pries them apart. Add up all the forms of energy, divide by the cosmic volume, and you get the number that tells you whether the universe curves, stays flat, or runs away screaming. Here's a simple way to picture it. Imagine tossing a ball straight up in the air. If you throw it too weakly, gravity pulls it back down. It collapses. That's like a positively curved universe. If you hurl it hard enough, it escapes forever, never turning back. That's a negatively curved universe. And if you throw it at the exact escape velocity, it keeps slowing but never quite stops. That's a flat universe. Cosmic density is the throw, gravity is the tug, and the universe is the ball. Cosmologists even gave this a neat symbol, O, omega. If O is greater than 1, the universe is closed and spherical. If O is less than 1, it's open and saddle-shaped. If O equals 1 exactly, space is flat. Simple math, infuriatingly difficult measurements. Now, here's the kicker. When scientists actually tried to calculate O, the result was alarmingly close to 1. Not vaguely close, suspiciously close, within a fraction of a percent. That's weird because the tiniest deviation in the early universe would have ballooned into something wildly different today. Picture trying to balance a pencil on its tip. Unless you have a trick, it's not going to stay upright for billions of years. The fact that our universe looks so flat now suggests there was some cosmic trick in play. Cue inflation, our miracle worker from earlier. But inflation aside, the idea of density shaping destiny has always haunted cosmology. If the universe had been denser, we might be living in a cosmos doomed to collapse, back into a fiery big crunch. If it had been thinner, galaxies might have flown apart so quickly that stars and planets never even formed. Instead, here we are, balanced in the middle lane, sipping coffee on a Tuesday, talking about cosmic fates like we had any say in them, and density doesn't just decide geometry. It also hints at the future. A flat or open universe tends to expand forever, especially with dark energy accelerating the process. A closed one might, in principle, recollapse. Though with dark energy in the mix, even that storyline gets messy. The point is, O is more than a statistic. It's a forecast. It's the universe's long-term weather report. So, what do the actual observations tell us? When scientists pointed their instruments at the oldest light in the cosmos, the cosmic microwave background, they weren't just measuring a faint afterglow, they were measuring the very curvature of space itself. And the results? Let's just say they made the case for a flat universe almost impossible to ignore. That detective story, how ancient light whispered the geometry of everything, is where we go next. All right, time to get playful. Because even if the universe is flat, that doesn't mean it's boring. Geometry isn't the whole story. Topology, the way space is stitched together, might still surprise us. Flatness doesn't rule out weirdness. In fact, it invites it. Here's where things get fun. A universe can be flat and still be finite if it's wrapped in the right way. Think of an old-school video game, like Pac-Man. You steer your little chomping circle off the right side of the screen and boom, you reappear on the left. The game map isn't infinite, it just loops. That's what cosmologists mean when they talk about a torus universe, shaped like a three-dimensional donut. Walk in a straight line long enough, and instead of hitting an edge, you pop back where you started. A donut universe. Tell me that isn't the most comforting mental image. Infinite coffee to go with it. But donuts aren't the only possibility. Space could be a kind of 3D lattice, where moving far enough in one direction makes you reappear somewhere unexpected. Like walking through a cosmic hall of mirrors. These strange topologies would make the universe finite but edgeless, looping back on itself in ways our instincts aren't built to handle. And here's the wild part. If space really were stitched together like that, we might catch the pattern in the sky. Light could circle around the cosmos, showing us multiple images of the same galaxy from different angles. It'd be like standing in a mirrored funhouse, where every direction shows a slightly different version of you. In theory, we could detect these cosmic copies if we spotted repeating patterns in the distribution of galaxies or in the ripples of the cosmic microwave background. So far, nothing. No mirrored patterns, no repeating galaxies waving back at us like déjà vu. That suggests if the universe is finite and looped, it's so large that the loops happen far beyond what we can see. From our little bubble, it might as well be infinite. But just the possibility that we live in a donut or a Pac-Man grid or some other playful topology is a reminder of how weird the universe could be without breaking any rules. It doesn't need walls. It doesn't need an outside. It could still be finite, but stitched in ways that turn geometry into trickery. And as strange as all this sounds, it's only the prelude to the real detective work. Because to test whether the universe is spherical, saddle-shaped, flat, or something looped and twisted. We need evidence, not just metaphors, not just thought experiments. We need to look at the oldest light in existence, the cosmic microwave background, and let it tell us what shape the universe has been hiding all along. That's where we're heading next, the universe's baby picture, and how scientists learn to read its wrinkles like a map of everything. All right, time to roll out the oldest photograph in existence, the universe's baby picture. About 13.8 billion years ago, when the cosmos was barely a toddler at 380,000 years old, it cooled enough for atoms to form. Before that, everything was a hot plasma soup where light couldn't travel freely. Photons kept bouncing around like drunk pinballs. But once atoms locked together, the fog lifted and light finally broke free. That ancient light is still around today, stretched by expansion into the faint microwave glow we call the cosmic microwave background, or CMB. Think of the CMB as wallpaper plastered across the entire sky. To the naked eye it's invisible, but with the right instruments it's everywhere, like static on an old television. And here's the kicker, the CMB isn't perfectly smooth. It's sprinkled with tiny temperature fluctuations, just millionths of a degree different from place to place. Those tiny wrinkles are pure gold, because they carry information about the shape and structure of space itself. How does that work? Imagine drawing circles on a balloon and then inflating it. From close up they look one size. From farther away their apparent size depends on how the surface curves. Same principle with the CMB. The hot and cold blotches in the microwave sky act like rulers. If the universe is positively curved, spherical, the blotches look larger than expected because space bends inward. If it's negatively curved, saddle-shaped, they look smaller because space bends outward. And if it's flat, they appear exactly the size theory predicts. So cosmologists built instruments to measure these blotches with absurd precision. First came ground-based and balloon experiments. Then in 1989, NASA launched COBE, the Cosmic Background Explorer. COBE's data was groundbreaking, showing the first evidence of those temperature ripples. Later missions like WMAP 2001 and ESA's Planck Satellite 2009 sharpened the picture. By mapping the entire sky in microwaves, they gave us a cosmic fingerprint, a snapshot of the universe when it was still a baby wrapped in a blanket of plasma. The results? Astonishing. The patterns in the CMB matched the predictions of a universe that is almost perfectly flat. The blotches weren't distorted into exaggerated largeness or shrunk into tiny freckles. They were just right, Goldilocks style. And not only that, but the CMB also carried hints about the universe's age, composition and expansion rate. It's as though the cosmos left behind a baby book with all the vital stats filled out. This was a turning point. For decades, the question of curvature, sphere, saddle or flat, was an open philosophical debate. Suddenly it became measurable. Suddenly we weren't speculating in smoke-filled rooms. We were reading the universe's own handwriting across the microwave sky. But the CMB doesn't just tell us about shape. It whispers secrets about density, dark matter, and dark energy too. Those tiny ripples were the seeds of all future structure, amplified over billions of years into galaxies and clusters. Every star you've ever seen, every planet, every one of us traces its ancestry back to those baby ripples frozen into the CMB. And the conclusion from all this detective work? Our universe is astonishingly flat. Not perfectly, not exactly, but so close to flat that if there is any curvature, it's hiding beyond our current ability to measure. That verdict in turn ties right back into cosmic inflation, the theory that stretched out the early universe so much that any initial curvature was ironed away. So the CMB gave us the first solid evidence of our universe's geometry, but it also handed us a mystery. Why is it so flat? That's the flatness problem. And it will drag us deeper into inflation, dark energy, and the tantalizing possibility that our universe is just one bubble in a bigger cosmic froth. So, what did the baby picture of the cosmos whisper to us? When scientists finally decoded the wrinkles of the cosmic microwave background, the answer was loud, clear, and a little eerie. The universe is flat. Not flat like conspiracy videos about Earth's shape. Flat in the geometric sense. The data from WMAP and later the Planck satellite showed that the large-scale curvature of space is so close to zero, it might as well be balancing on a razor's edge. Parallel lines don't curve inward like on a sphere, and they don't splay apart like on a saddle. They run side by side indefinitely. And this wasn't a sloppy measurement. Planck's results narrowed the margin of error down to ridiculous levels. If there is any curvature at all, it's smaller than 0.2%. That's like measuring the width of Earth and finding it deviates from perfect roundness by less than the thickness of a sheet of paper. In cosmic terms, it's shockingly precise. Flat space means Euclidean rules still apply, even across billions of light years. Triangles add up neatly to 180 degrees. The Pythagorean theorem holds true, whether you're drawing it on paper or building it out of galaxies. On the grandest scale, the universe behaves like the geometry you learned in middle school. But here's where the unease creeps in. Flatness isn't the default state. It's unstable, like trying to balance that pencil on its tip. Over billions of years, the tiniest deviation should have snowballed into obvious curvature. Yet here we are, in a universe that looks flatter than your phone screen. Coincidence? Probably not. Enter cosmic inflation, the universe's way of stretching itself so much, so fast, that any original curvature was ironed out like wrinkles in a sheet. Flatness also has consequences. In a flat universe, there's no natural boundary, no built-in edge. It suggests the cosmos could be infinite in extent, even if our observable bubble is finite. Flatness doesn't guarantee infinity, but it leaves the door wide open, and the idea of an infinite universe fits uncomfortably well with the numbers we see. And then there's the forecast. A flat cosmos with dark energy in the driver's seat isn't headed for a neat collapse or a quiet coast. It's headed for endless expansion, accelerating into a future where galaxies vanish from sight, the night sky grows dark, and the observable universe becomes a lonely island. Flatness isn't just geometry, it's destiny. So, the CMB gave us our answer. The universe is as flat as human instruments can measure. But that answer comes with a new riddle. Why is it flat? Why did the early universe tune itself so precisely to this balance point? Inflation is the leading suspect, but it drags along its own set of mysteries, and even whispers about multiverses, bubbles, and realities beyond our own. And that's where we're heading next. The flatness problem. Why the universe's shape is so suspiciously perfect, and how cosmic inflation swoops in to play both savior and troublemaker. So, the verdict is in. Our universe is flat. Not sort of flat, not close enough, but flat to within a fraction of a percent. And that, my friend, is deeply suspicious. Here's why. Flatness is not a stable condition. Imagine trying to balance a pencil on its tip. In theory, it's possible. In practice, the slightest nudge, the tiniest breath, and it tips over. Now imagine that pencil somehow staying perfectly balanced for 13.8 billion years. That's the cosmic equivalent of what we're seeing. If the universe had started with even a whisper of extra density, gravity would have pulled it inward, curving space like a sphere and possibly dooming it to a big crunch. If it had started with just a touch less density, expansion would have pulled it outward like a saddle, racing galaxies away before stars and planets could form. Yet, against all odds, the numbers line up to give us a universe that is still flat today. This puzzle is called the flatness problem. And it's not just an academic quirk. It's a screaming neon sign that something extraordinary must have happened in the early universe. Because the only way to explain such precision is that the conditions of the Big Bang were tuned to a degree that feels absurd, too absurd for coincidence. Enter cosmic inflation, stage left. Inflation theory says that in the tiniest fraction of a second after the Big Bang, the universe expanded at an exponential rate, smoothing and stretching everything so drastically that any initial curvature was flattened out. It's like blowing up a balloon so much that from where you stand the surface looks flat. Inflation took whatever jagged, wrinkled geometry existed at the beginning and ironed it smooth across scales we can never hope to see. Problem solved? Well, sort of. Inflation explains flatness beautifully, but it also raises awkward questions. Why did inflation start? Why did it stop? Did it happen everywhere, or only in our patch of reality? Some versions of the theory suggest inflation might still be happening elsewhere, spawning new universes like bubbles in an endless cosmic froth. If that's true, then our flat, finely tuned universe might just be one bubble among infinitely many, each with its own geometry, physics, even laws of nature. That's the multiverse idea. Controversial, tantalizing, and so far untestable. Some physicists love it, others roll their eyes. But whether or not you buy into bubble universes, inflation remains the leading explanation for why our cosmos is so astonishingly flat. Without it, we'd be stuck shrugging at a coincidence too extreme to take seriously. So flatness isn't just a geometry lesson, it's a clue, a hint that the universe had a violent dramatic growth spurt that set the stage for everything that followed, and it's not the only clue inflation leaves behind. It also predicts that quantum jitters, microscopic fluctuations in energy, were blown up to cosmic size, seeding the galaxies and clusters we see today. That's right, your very existence is built on amplified quantum noise. Flatness, then, isn't just about shape, it's about origins. It tells us something extraordinary happened in that first instant, a process so powerful it smoothed the cosmos, set its density with impossible precision, and maybe even hinted at realities beyond our own. And if that doesn't already keep you awake at night, the next part will. Because once you accept flatness, you have to face its consequence, scale. If the universe is really this flat, then it's probably not just big, it's much bigger than we can see, possibly hundreds of times bigger, maybe infinite. And that means our 93 billion light-year bubble is just the tiniest window into a cosmos far more vast than our imagination can bear. All right, let's stretch our necks a little, because flatness carries with it a staggering implication. The universe is way bigger than what we can see. We already know our observable universe spans about 93 billion light-years across. That number alone should make your brain want to lie down. But here's the twist. That's just our horizon. Beyond it, space doesn't politely stop. It keeps going. And if flatness is real, then the universe doesn't just keep going a little bit. It could be hundreds, thousands, or even trillions of times bigger than our bubble, maybe infinite. Think about standing on the shore of the ocean. You see the horizon curving away, but you know the sea doesn't stop there. The waves keep rolling far beyond your sight. Now swap the ocean for galaxies, and the horizon for the edge of our observable universe. Same deal, except instead of a few hundred more miles of water, we're talking about unfathomable stretches of space, maybe populated by structures we'll never detect. Some estimates suggest that the whole universe could be at least 250 times larger than the observable slice. 250 times. That's like thinking you've explored the whole Earth because you walked around your backyard. In terms of volume, that's not just bigger. It's bigger by a factor of 100 million, and that's the conservative take. If the universe is infinite, then those numbers are meaningless. There's no edge, no cutoff, no boundary. Just galaxies and stars and gas and voids, forever. Every telescope we build, every future space probe, every clever technique, will still be stuck in our bubble. Because no matter how advanced our tools become, light from beyond the horizon will never reach us. Not now, not in 1 trillion years. Here's the kicker. Despite that limitation, science is still confident about this bigger picture. Why? Because flatness itself is a clue. Just like you can tell Earth is round without sailing every ocean, you can infer that the universe is vast without seeing all of it. The fact that it appears so flat over such an enormous scale suggests it continues smoothly beyond the part we can observe. And that has consequences for how we see ourselves. When we call our galaxy a speck, it's not poetic exaggeration. It's literal. The Milky Way, with its 200 billion stars, is one of 2 trillion galaxies in the observable universe. And if that's just the tiny patch we can see, then the true total, beyond counting, beyond meaning. But the scale question doesn't stop at size. If the universe is this vast, then it doesn't just repeat structures, it might repeat histories. In a space big enough, probability demands duplication. Somewhere out there, maybe impossibly far away, there could be another region where history played out almost identically to ours. Another Earth, another you. Infinity makes even the wildest scenarios inevitable. And that's why the next step in our journey gets strange. Because if space really is infinite, then we're forced to grapple not just with size, but with the unnerving concept of duplicates. Cosmic doppelgangers walking around in galaxies we'll never see. If infinity made your stomach flip, brace yourself. Because the math of an infinite universe doesn't just suggest endless stars. It whispers something far more unsettling: endless copies of you. Here's how it works. In physics, matter is finite in arrangement. There are only so many ways atoms can be shuffled within a region the size of our observable universe. The number is huge, ridiculously, astronomically, mind-meltingly huge, but still finite. Now take that finite number of possibilities and spread it across an infinite cosmos. Eventually the combinations have to repeat. Just like rolling dice long enough guarantees doubles, infinity guarantees duplication. That means somewhere out there, in a galaxy unimaginably far away, there could be a planet almost identical to Earth. On that planet, a version of you is watching this exact video. Another version clicked away halfway through. Another never got into history videos at all and became a semi-professional llama wrangler. Infinite universes mean infinite rollouts of possibility. It's not science fiction, it's statistics. If the universe is truly infinite and governed by consistent physical laws, then every arrangement of matter, every possible history must exist, and not just once. Infinitely many times. Unsettling? Absolutely, because it rubs against our sense of uniqueness. We like to think of our lives as singular, unrepeatable stories. Infinity shrugs and says, "Sure, but I've got countless reruns." But here's the flip side. Those duplicates don't cheapen this you. Just because another version of you might exist doesn't make your choices less real. It only underscores how absurdly vast reality is, that it can contain every possibility and still leave room for more. Your life is still your own thread in the cosmic tapestry. The fact that infinity might weave parallel threads doesn't erase the beauty of this one. And it's worth pausing here, because this isn't just a physics problem, it's a philosophical one. If infinite duplicates exist, what does that mean for free will, for identity, for meaning? If another you is out there making different choices, does that lessen your responsibility here? Or does it make your existence even more precious? Because somehow, against all odds, you're aware of this particular moment. Physicists don't lose sleep over the moral implications, but they do wrestle with the science. We don't know for sure if the universe is infinite. Flatness strongly suggests it, but the evidence is indirect. It's possible the cosmos is merely enormous, so huge that for all practical purposes it feels infinite, even if it technically isn't. In that case, the probability of duplicates drops to near zero. But if infinity is real, then it isn't just stars that repeat. It's lives, it's histories, it's choices. And that turns the night sky into a hall of mirrors, where every flicker of starlight might carry the echo of a version of you wandering beneath an alien sun. Infinity forces us to stretch not just our imagination, but our sense of identity. And as unsettling as it is, it might also be liberating. Because if the cosmos is big enough for infinite versions of you, then it's also big enough to hold infinite meaning. Still, let's zoom back from philosophy to physics. If duplicates are possible, what else could an infinite cosmos contain? Worlds where physics itself plays by slightly different rules, reality stitched together in ways we've barely begun to imagine. To chase those questions, we need to peer into the frontier where cosmology blurs into speculation. The multiverse. Alright, so we've tiptoed up to the edge of infinity and stared at the unsettling possibility of duplicates. Now it's time to take a step further into the rabbit hole, the multiverse. The multiverse isn't one single idea. It's a cluster of overlapping, sometimes competing theories. But they all circle the same provocative thought. Maybe our universe isn't the only one. Maybe it's just one bubble in a frothy sea of countless others, each with its own properties, its own histories, maybe even its own laws of physics. Let's start with the version that ties directly into inflation. Remember that wild growth spurt at the dawn of time? Some physicists argue inflation didn't stop everywhere at once. Instead, it might have sputtered, ending in some regions, continuing in others. Where it ended, universes like ours formed. Where it kept going, new pockets inflated, each blossoming into a separate universe. This scenario, called eternal inflation, imagines the cosmos as a constantly frothing ocean of bubble universes, forever spawning new bubbles. Inside our bubble, the speed of light, the charge of the electron, the strength of gravity, these numbers look fixed. But in another bubble they might be slightly different, or wildly different. Some bubbles could collapse instantly, others might never form galaxies, and a few, like ours, might be tuned just right for stars, planets, and eventually curious creatures asking late-night questions about cosmic geometry. But inflation isn't the only road to the multiverse. Quantum mechanics suggests another, the many worlds interpretation. In this view, every time a quantum event has multiple outcomes, the universe splits, with each outcome realized in a branching reality. Flip a coin. Its heads in one universe, tails in another. In one branch you're listening to this video, in another you paused it and never came back. An infinite branching tree of possibilities. And then there's the idea that the laws of physics themselves might allow for higher dimensional universes. Realities stacked alongside ours like pages in an invisible book. Some versions of string theory hint at this, imagining our universe as a three-dimensional brain, floating in a higher dimensional space. Collisions between brains could even spark big bangs, birthing new universes like sparks flying off steel. Now, let's be clear, the multiverse is speculative, beautiful, tantalizing, but speculative. We don't have direct evidence for other universes. By definition, they lie beyond our cosmic horizon. But here's the catch. Sometimes the math demands it. Inflation explains too much too well to ignore, and one of its side effects is a multiverse. The flatness, the uniformity, the structure of galaxies all fit neatly once you allow for inflation. And if inflation is real, the multiverse might come with it as part of the package. So what do we do with that? Some physicists embrace it, seeing the multiverse as the ultimate context. Our universe isn't fine-tuned by magic, it's just one lottery winner in an endless draw. Others bristle, arguing that a theory you can't test is philosophy, not science. The debate rages on. But whether you accept it or not, the multiverse idea forces us to reframe the question. Instead of asking, why is the universe flat? Why are the constants of physics so precise? We might instead ask, why wouldn't they be? If there are countless universes with countless properties, then it's no surprise that one of them happens to be just right for life, and it just happens to be the one we're in. It's a dizzying thought. We're not just small fish in a big pond. We might be fish in one bubble of an infinite boiling ocean, surrounded by other bubbles we'll never see. And yet, somehow, the mystery only makes our little bubble feel more precious. Next, we'll dive deeper into this. How physicists argue about the multiverse, what evidence they're hunting for, and why the very idea stretches the definition of science itself. Alright, so the multiverse sounds like a late-night dorm room idea stretched to cosmic proportions. But in modern physics, it's not just a stone-of-thought experiment, it's a genuine debate. The question is, does the multiverse count as science, or is it just philosophy dressed in equations? Here's the crux of the problem. Science, at its core, depends on testability. A claim is scientific if we can, in principle, design an experiment or observation to confirm or falsify it. But by definition, other universes, if they exist, are outside our observable bubble. No telescope can peek across into a neighbouring universe. No spacecraft can punch through the cosmic horizon. That makes the multiverse maddening. It's a theory that explains a lot but hides its receipts where we can't reach them. This is why some physicists bristle at it. They argue that without direct evidence, the multiverse belongs in the same category as untestable metaphysics. Others counter that indirect evidence is enough. If inflation theory predicts the multiverse, and inflation explains real, observable phenomena, like flatness, uniformity, the distribution of galaxies, then the multiverse is a natural extension of that success. You don't have to see the other universes, you just need to follow the logic. Think of it like this. We've never seen the inside of Earth's core, but we accept models of it, because seismic waves and gravity tell us it's there. Similarly, we may never see other universes, but if all our best theories point toward their existence, ignoring them would be willful blindness. Still, the debate is fierce. Some scientists see the multiverse as a cosmic get-out-of-jail card. Don't know why the constants of physics are what they are. Don't worry, there are infinite universes, and we just happen to be in the one that works. Problem solved. Others say that's a cop-out, the physics equivalent of throwing up your hands and saying be because magic. But here's the quiet truth. Even skeptics admit the multiverse idea is useful. It reframes the problem of fine-tuning. Instead of asking, why is the universe so perfectly set up for life, the multiverse asks. Why wouldn't it be, if countless universes exist? It doesn't answer the question so much as dissolve it. Whether that's satisfying or infuriating depends on your appetite for mystery. And then there's the cultural side. Humans have always dreamed of other worlds. From myths of mirror realms to medieval tales of infinite heavens, we've never been comfortable with just one reality. The multiverse is science's version of that ancient longing, dressed in math instead of myth. For now, the multiverse sits in a liminal space, half science, half philosophy, with one foot in testable predictions and the other in speculation. Some physicists bet their careers on it, others scoff, but the debate itself shows how strange cosmology has become. We're not just measuring stars anymore. We're wrestling with the definition of reality itself, and if that feels like the edge of what humans can handle, brace yourself. Because the next step isn't about physics at all, it's about meaning. If the multiverse is real, what does that do to our sense of purpose, our place in the cosmos, and the story we tell ourselves about why we exist at all? So let's say, just for the sake of argument, the multiverse is real. Infinite bubbles, infinite histories, infinite versions of everything. What does that do to us, to our sense of meaning, of purpose, of uniqueness? At first, it can feel crushing. If there are infinite Earths, infinite versions of you making every possible choice, then doesn't that make this version meaningless? Aren't you just one copy in an endless hall of mirrors? But pause. Meaning isn't about rarity. A rainbow isn't less beautiful because countless rainbows have arced across the sky before. A song isn't worthless because it can be replayed. Meaning lives in experience, not statistics. You're the only version of you that feels this moment. That's what makes it real. And in a strange way, the multiverse can deepen meaning. If infinite possibilities exist, then your awareness of this particular one becomes astonishing. Out of all the universes, you landed here, in this body on this planet, watching this story unfold. That's not meaningless. That's miraculous. Philosophers have long wrestled with this. In medieval times, some argue that God must have created infinite worlds, because an infinite being wouldn't stop at one. Others argued the opposite, that our world is unique, chosen, special. The multiverse reignites that ancient debate in scientific clothing. Do we find comfort in infinite abundance, or despair in our smallness? The answer depends on what story we choose to tell ourselves. And here's the irony. Even if duplicates of you exist, they don't cheapen your choices. They amplify them. Because your choices ripple out in this thread of reality. The fact that another you may have chosen differently doesn't undo the courage or kindness or curiosity of this you. Each path matters on its own terms. Think about how we already live with echoes. You've probably thought about the what-ifs of your own life. What if I'd taken that job, married that person, moved to that city? Those are parallel universes of a sort imagined in your mind. The multiverse just takes that thought experiment and says, hey, maybe those paths are real somewhere out there. But they don't change the ground under your feet. They just remind you how wildly open reality might be. So meaning in a multiverse isn't lost. It's reframed. It's not about being the only one. It's about being this one, about savouring the improbable fact that you're alive in this universe with its physics, its stars, its history, and its questions. Out of all possible realities, you got this one, and that's enough to take your breath away. All right, enough with cosmic doppelgangers. Let's come back to the universe we can actually measure. Because while we've been staring at flatness, infinity, and speculative bubbles, the cosmos has been busy playing another trick. It's not just expanding, it's accelerating. And that acceleration is driven by something we call dark energy. The story begins in the late 1990s, when astronomers studied distant supernovae, exploding stars bright enough to act as cosmic lighthouses. By measuring their brightness, scientists could tell how far away they were. By measuring their redshift, they could tell how fast the galaxies hosting them were receding, the expectation. The expansion of the universe should be slowing down, thanks to gravity. The shock? It wasn't slowing, it was speeding up. That discovery, in 1998, earned a Nobel Prize, and it upended our picture of the cosmos. Something was pushing galaxies apart, stronger than gravity's pull. That something was labelled dark energy, a placeholder term for whatever invisible pressure is stretching space itself. And according to current measurements, dark energy makes up about 70% of the total energy in the universe. That's right. The majority of reality is something we don't understand, a ghostly repulsion humming through the fabric of space. So what is it? The simplest explanation is the cosmological constant, an idea Einstein first proposed and then abandoned. It's the energy of empty space itself. The vacuum has weight, so to speak, and that weight pushes outward. But other theories suggest it could be something more dynamic, like a field that changes over time, or even a sign that our understanding of gravity is incomplete. For now, dark energy is less an explanation and more a label for a mystery. But whatever it is, it controls the fate of the universe. If dark energy stays constant, space will keep stretching forever, galaxies drifting apart until the night sky grows empty, stars die, and everything ends in a big freeze, a silent, cold eternity. If dark energy grows stronger over time, it could end in a big rip, tearing galaxies, stars, planets, and eventually atoms apart. If somehow it weakens or flips, it could allow gravity to win, leading to a big crunch where the cosmos collapses back into fire. Right now, the data leans toward the big freeze, endless expansion, stars winking out one by one until even black holes evaporate into the background. It's not the most cheerful ending, but it's the one written in the math we have. And yet, just like with flatness, we have to pause and marvel. Think about it. We live in a universe where most of reality is invisible, where the very force shaping our destiny is something we can barely describe. Dark energy is both terrifying and humbling. It reminds us how much we don't know. Our best telescopes have shown us the grand stage, but the script is still half erased. So, as the curtain of dark energy spreads wider, we're left with a haunting question. If this expansion is the law of our cosmos, does that mean every universe, if the multiverse exists, is ruled by its own version of dark energy too? Do other bubbles have their own fates? Some freezing, some collapsing, some tearing apart? That's where our journey takes us next, into the ultimate speculation, the possible endings of everything, and what they tell us about the strange temporary moment we inhabit right now. All right, let's lean all the way in. If the universe has a beginning, and inflation, the Big Bang, and the CMB all shout that it does, then what about the end? Cosmologists have sketched out a few candidates, and none of them are particularly comforting bedtime stories. 1. The big freeze, heat death. This is the leading contender, the one the math currently favours. Dark energy keeps pushing, galaxies keep drifting, and eventually every star burns out. New stars stop forming. The night sky goes dark as galaxies slip beyond our cosmic horizon. Black holes swallow what's left, but even they aren't eternal. Over unimaginable time spans, they evaporate through Hawking radiation. What's left? A cold, thin soup of particles, spread so far apart that nothing ever happens again. Eternity, but boring. 2. The big rip now. Imagine dark energy doesn't stay constant. Imagine it strengthens. Expansion accelerates so much that first galaxy clusters, then galaxies, then solar systems are torn apart. Eventually, even atoms themselves can't hold together. Space stretches until there is literally nothing left to stretch. The clock ends not with a whisper of cold, but with everything shredded into raw energy. 3. The big crunch. This one's the mirror opposite of expansion. If somehow dark energy weakens or reverses, gravity could take back control. Galaxies would stop receding and begin collapsing inward. Stars and galaxies would merge in fiery collisions. Eventually the universe would shrink back to a hot, dense point, maybe to rebound in another bang, maybe to end in silence. It's poetic, but current data suggests it's unlikely. 4. The big bounce. A cousin of the crunch, the idea that collapse leads not to finality but to rebirth. The universe could oscillate. Big bang, expansion, collapse, repeat. Eternal cycles of birth and death, with each round wiping the slate clean. Some cosmologists like this for its symmetry. Others dismiss it as wishful thinking. 5. Vacuum decay, the most unsettling. Then there's the wild card straight out of particle physics. The universe might not be in its most stable state. If our vacuum is false, it could, without warning, tunnel into a lower energy state. That transition would spread at near the speed of the light, rewriting the laws of physics as it goes. No warning, no escape. One moment you're sipping coffee, the next, poof. Not with fire, but with a quiet reprogramming of reality itself. Comforting? Not really. Now, which ending do we get? Nobody knows. Current evidence points toward the big freeze, but the truth is, we don't have enough information to be certain. Dark energy, the very force driving our fate, is still a mystery. The future of everything hangs on something we don't understand. But here's the thought that lingers. Whichever ending awaits, we're alive in a unique sliver of cosmic history. Stars are burning, galaxies shine, life is possible. We exist in a brief golden window between the fiery chaos of the beginning and the silent destiny of the end. Out of all the possible moments, this is the one we got. And that realization that we live in a fragile, temporary now might be the deepest meaning cosmology offers. Next, we'll turn back from the ending to the present. What this knowledge does to our perspective, how seeing the fate of everything reframes the way we live on our small blue planet today. So here's the strange, poetic truth. We are living in the middle of the story, not at the fiery beginning, not at the silent end. Right now, the universe is in its prime, galaxies blazing, stars burning, life sprouting on at least one small blue planet. We exist in what cosmologists sometimes call the stelliferous era, the age of stars, and that makes our moment extraordinary. Think about the timeline. The Big Bang happened 13.8 billion years ago. Stars began forming a few 100 million years later. Since then, galaxies have clustered, planets have spun into being, and chemistry has played dice until, eventually, consciousness arose to ask, what is all this? But here's the kicker. This golden age won't last forever. Stars are temporary. Galaxies evolve. Dark energy is pulling the stage wider and wider apart. Someday, not all that far in the future by cosmic standards, the skies will grow empty. A few trillion years from now, if any creatures are still around, they'll look up and see no galaxies beyond their own. They'll have no evidence of a Big Bang, no cosmic microwave background, no grand story of expansion. Their night will be lonely and silent. We, on the other hand, are here at the sweet spot. We arrived just late enough that the universe has matured into a complex, life-friendly place. Heavy elements forged in dying stars, planets with atmospheres, chemistry robust enough to build DNA. And we arrived just early enough that the cosmic signals are still visible. The microwave afterglow, the galaxies racing apart, the fingerprints of inflation. We can actually reconstruct the story of the universe in a way no future civilization will be able to. That's wild, isn't it? Out of billions of years, we landed right here, in the narrow window when the universe is both habitable and understandable. We are children of a rare middle chapter, and maybe that's why cosmology matters so much. When we trace the universe's fate, big freeze, rip, crunch, or bounce, it's not about predicting doom. It's about recognizing how fragile and miraculous this moment is. It's about realizing that the stars overhead are temporary, and so are we, and that knowledge gives our lives a sharper edge of meaning. You could say we are cosmic archaeologists digging through light and gravity to piece together a story written billions of years ago. A story that will fade from the record in the eons to come. Our work, our curiosity, might be the only chance the universe has to know itself before the evidence disappears. So living in the middle chapter isn't depressing, it's exhilarating. It means we are here at the only time the cosmos is legible. The universe is a book, and we just happen to be alive on the one page where the words can still be read. And with that perspective in mind, we're ready for the final question in this journey. If the universe has no edge, no centre, and maybe no end, what does that mean for our place in it? Are we insignificant? Or are we more important than ever for being the universe's brief moment of self-awareness? Here's the thing cosmology keeps hammering home. Whether we like it or not, the universe has no special seat reserved for us. No centre, no edge, no front row. Every observer, wherever they are, sees themselves as the middle of their observable universe. From our perspective, Earth sits in the centre of a 93 billion light-year bubble. But a galaxy 20 billion light-years away would say the same about itself. It's not that we're wrong, it's that everyone is right. The cosmos is democratic like that. There is no privileged vantage point. The balloon expands, but every ant crawling on it feels like it's at the middle. We are ants on the balloon. That's humbling. For most of human history, we placed ourselves at the centre, first of the Earth, then the solar system, then the galaxy. Every time, science pulled the rug out. And now, on the grandest scale, the verdict is final. There is no cosmic throne. We are not the hub of the wheel. We are one spoke among countless others. But here's the twist. That doesn't make us insignificant. If anything, it makes us more astonishing. Because in a universe with no centre and no edge, consciousness itself becomes rare. Out of endless voids, collapsing stars, and mindless physics, something emerged that can notice. You, me, all of us. We are the eyes of a blind cosmos, the neurons firing in a mindless sea of matter. And think about what that means. Every time you look at the night sky, you're not looking out from the centre. You're looking out from one random perch, one bubble among countless others, and yet, those galaxies, those ancient photons, tell a story you can actually read. You don't need a throne at the centre to matter. You only need awareness. The lack of a cosmic centre doesn't diminish us. It democratizes existence. Every corner of the universe, every galaxy, every observer, each gets the same privilege of seeing the cosmos expand from their own horizon. In a way, everywhere is the centre, because everywhere is equally woven into the fabric of space-time. So here's the paradox. The universe makes us feel small, but it also gives us the ultimate intimacy. You're not at the edge, because there is no edge. You're not off-centre, because there is no centre. Wherever you stand, you are woven into the heart of it all. And that realization carries us toward the final stretch of our journey. Not the physics, not the geometry, but the philosophy of awe. What does it mean to live, not at the centre of the universe, but inside a universe where every point is central. So after all the math, the measurements, the grand diagrams of expansion and curvature, what are we left with? Awe. That quiet, almost electric feeling that sneaks up on you when you realize the universe doesn't owe you an explanation. And yet, somehow, it has given you one anyway. Think about it. We live in a cosmos without edges, without a center, without a throne. It's flat as far as we can measure, expanding faster than we can chase, and governed by dark energy we barely understand. On the face of it, that should make us feel small, and it does. But awe isn't about size, it's about perspective. Because the miracle is not that we're insignificant. The miracle is that we are here. Against impossible odds, in a universe governed by indifferent physics, matter learned to ask questions. Hydrogen atoms, forged in the first minutes after the Big Bang, eventually assembled into stars, then into carbon, then into DNA, then into neurons. And now those neurons are sitting here, late at night, whispering about the shape of the universe. That's awe. And awe does something sneaky. It reframes despair into humility. The idea that we are one speck in an infinite void can sound crushing. But humility doesn't have to be defeat. It can be liberation. If the universe is vast and endless, then your life isn't meaningless. It's woven into a story too big to ever finish. You don't have to carry the weight of cosmic importance. You only have to exist, to notice, to feel wonder. Cultures have known this long before cosmology gave us equations. Ancient poets wrote of the heavens declaring the glory, of the stars as witnesses to something beyond comprehension. The Greeks spoke of the cosmos as ordered beauty. Philosophers across eras have all bumped into the same truth. The human heart responds to vastness not with calculation, but with reverence. And maybe that's the most precious outcome of all this science. Not the numbers, not the charts, but the shift in how we see ourselves. Awe doesn't demand certainty. It thrives on mystery. It teaches us that not knowing is not failure, it's invitation. So here's the takeaway. The universe has no edge, but awe is the edge of human experience. It's the frontier where knowledge ends and wonder begins. And standing there, between what we know and what we can't, is where we feel most alive. Next, we'll bring everything home, we'll tie together the science, the speculation, and the awe, and leave with one final thought about what it means to live in a cosmos that has no end, no edge, and no final answer. So where does this leave us? We've wandered from the edge of the observable universe to the possibility of infinite duplicates, from the wild burst of inflation to the slow death of stars, from cosmic geometry to the philosophy of awe. And now, at the end of our journey, the strangest truth is also the simplest. The universe may not have an end, but our time inside it does. That contrast, the infinite and the fleeting, is the heart of the story. The cosmos doesn't need an edge or a center to be breathtaking. It's breathtaking because we, fragile creatures of dust and carbon, get to stand inside it and ask questions. We are temporary, but our questions stretch far. We are small, but our curiosity has no limit. In that sense, we reflect the universe itself, bound in time, but reaching for eternity. So let's return to the original itch. Does the universe have an edge? The answer, as best as science can give, is no. Not in the way you think of an edge. No walls, no cosmic fences, no here be dragons carved into the sky. The only edges we know are the limits of light, the boundaries of what we can see. Beyond that, the cosmos goes on, whether as a looping sphere, an endless flat plane, or an infinite froth of universes bubbling forever. And maybe that's the most liberating answer of all, because an edge would be comforting, something to point to, something that says, here's the boundary. But no edge means no limits. It means possibility without end. It means there is always more to learn, more to see, more to wonder about. So what do we do with that? We live. We look up at the stars and know they are temporary, just like us. We ask questions, even when answers are incomplete. We tell stories, not because they finish the mystery, but because they let us share in it. And maybe that's the quiet meaning the universe offers. Not certainty, but participation. The cosmos doesn't need us. But here we are anyway, awake in its middle chapter, whispering to each other about infinity. That's not nothing. That's everything. And so, after all this, if someone asks you what lies at the edge of the universe, you can smile and say, the edge isn't out there, it's in here. It's the limit of our sight, the frontier of our imagination, the horizon of our questions. And beyond it, the story just keeps going.